Right, so for the short answer section, metal sphere labelled S1 carries 8 microcoulombs of positive charge. The radius of the sphere is not significant, so S1 may be considered the point charge. Second similar sphere labelled S2 without any charge, so 0 coulombs, is placed at a distance 5.8 centimetres. Okay, both spheres are held in place with perfectly insulating rods. The magnitude of the electrical force exerted by S1 on S2, well, that's going to be 0 newtons, simply because F equals KQ1 Q2 over R squared, and that's 0. Sphere S2 is then brought into contact with sphere S1. After a few seconds, it's returned to its original position. What's the magnitude of the charge on S2 now? So if S1 originally had 8 microcoulombs, when it comes in touch, that 8 microcoulombs will be shared, and then when they're separated, you'll end up with 4 microcoulombs per sphere. Now, just be careful here, because this says millicoulombs in the answers. So that would become 4 by 10 to the neg 6 coulombs. So to convert that to milli, then that becomes 4 by 10 to the neg 3. 4 by 10 to the neg 3 millicoulombs. On figure 1 on the opposite page, draw an arrow from the centre of S1 to indicate the direction of the force, okay, and explain your answer. Righto, so just so we can see it here, S1, S2. Now, because they've both got the same charge, as in positive charge, it's going to be a repulsion. And because it's a repulsion, if we're after indicate the direction of the force that S2 exerts on S1, it's going to be out in that direction. So due to the same charge, due to same charge. Okay, question 2. Says a stationary loop of metal wire with cross-sectional area of 13.7 centimetres squared. Straight away that rings alarm bells for me, because a lot of students don't know how to convert centimetres squared to metres squared properly. 1 metre squared is equal to 10,000 centimetres squared. So 13.7 centimetres squared is equal to 13.7 by 10 to the negative 4 metres squared. Something to remember. Anyway, moving on. Here we have the electromagnet is initially switched off. The current that is used to generate the electromagnet is then varied such that the magnetic field strength. Okay, that's all good. Because we know that EMF is negative n change in flux over change in time, well, this is realistically equals negative n change in magnetic field A over change in time. We can see here that this is essentially the gradient. So this has got a positive gradient. So we're going to end up with a constant negative EMF. This one over here is constant negative EMF for the same reason. This one here is a negative gradient, so it's going to be a constant positive EMF, and the same for the other one. Here there is no gradient, so therefore we're going to have a 0 EMF. Okay, so now let's have a look. Sketch the EMF induced in the loop. Okay, so to start with, we've got 0, and we're going to come down, across, up. We're going to go up the same amount, okay, simply because the gradients on the previous one were the same magnitude. And then that one, and got to get the symmetry. Obviously in the exam you will have rulers, and that will be beautiful, but that's essentially what you get. Next one, the maximum magnetic flux through the loop. So maximum magnetic flux through the loop. Magnetic flux equals B A. So if we got a maximum to 0.06, that's equal to 0.06 times by the area that we just said before, and the area was 13.7 by 10 to the neg 4. 13.7 by 10 to the neg 4. Calculate that out, and it gives you 8.22 by 10 to the neg 5 Weber. So 8.22 by 10 to the neg 5. Right. Calculate the magnitude of the EMF generated. So for this one, the EMF, what was it? Let's get carried away, equals negative n change in flux over change in time. Single wire, so 8.22 by 10 to the neg 5 over change in time was 0.09, 0.09, and that gives us 9.1 by 10 to the neg 4 volts. So 9.1 by 10 to the neg 4. Alright, question 3. A U-shaped magnet, so horseshoe magnet, is used to study the effect of a magnetic field on a conductor carrying a current, as shown in figure 4. The conductor receives current from a pair of wires that are wholly outside the magnetic field of the magnet, so the current's going across that way. Magnetic field is going in that direction. Just like to get those in there. The current source is switched on and the conductor experiences a force due to the magnetic field of the magnet. Use the answer key to state the direction of the force on the conductor and explain your answer. So once again, use the right-hand slap rule. Fingers going up. Magnetic current going from my left to the right. So that means it's going to be coming out. So it's going to be coming out of the horseshoe. So it's going to be E. So for 2 marks. So use the answer key. So done that, and we need to explain. So using right hand slap rule, I to the right, B up gives F out of horseshoe, or something along those lines. Next part. B, the length of the conductor that is within the magnetic field is 6.5 centimetres. Once again, I'll always convert that. So L equals 6.5 by 10 to the neg 2 metres. Current through the conductor, 0.39 amps. Force meter, so F equals 7.3 by 10 to the neg 6 newtons. Determine the strength of the magnetic field. B equals question mark. So rearrange F equals B I L, and that gives us B equals F over I L. So B equals F 7.3 by 10 to the neg 6 over 0.39 by 6.5 by 10 to the neg 2. And that gives us a magnetic field then of 2.88 by 10 to the neg 4 Tesla. So 2.88 by 10 to the neg 4 Tesla.